So the outline is as follows. We will try to position the facility location within the current context of analytics. Then we will present the AIMS analytics platform, and next we will go into the modeling aspects for facility location, and we will provide a number of examples, representative examples. In the end, we will also provide more insight into the visualization options provided by AIMS for this type of problems. So analytics for location. Well, analytics is the new trend with the promise of making better decisions based on data analysis. There are famous books initiated by Thomas Davenport on this topic, Analytics at Work, for example, that present different application areas where applying analytics leads to smarter decision and better results. More recently, the book published by Dimitris Bersimas, The Analytics Edge, gives a very nice overview of the analytics field. The main idea is that the only objective reality in decisional problems is the reality of data, but models play an essential supportive role, and this model essence needs to be captured. The analytics maturity levels, so roughly speaking, we can distinguish between different levels of analytics: descriptive analytics, diagnostic analytics, predictive analytics, and well, let's say the most advanced level, prescriptive analytics. Prescriptive analytics is concerned with not only providing insight based on the data, but also providing recommended actions that can actually support the decision-making process. Then we come to the topic of today, facility location. This is an important field in operations research, analytics, and optimization, with a very solid theory, a rich collection of algorithms, and a very large area of applications. We can think here about transportation problems, network design, supply chain problems, or placing, for example, electronic components on a given board area. Eventually, all these problems can be effectively tackled using modeling and optimization. So we present mainly the optimization aspect as representative for prescriptive analytics, which can provide actionable insight into the decision-making process. AIMS is an analytics platform that can provide a lot of functionality. So AIMS is an integrated and interactive modeling system. It has means for modeling optimization, mathematical optimization problems, but also for visualizing the solution, and also for advanced deployment using either Windows-based user interface or web-based user interface. AIMS connects to commercial solvers for the solution of mathematical optimization problems. So in the modeling part, in the development part of AIMS, there are many functionalities. Of course, first of all, the model can be formulated, but it's not only about the model. There is a lot of information that can be managed around the model. There are very specific modeling constraints provided by AIMS that can ease the task of formulating the model, running the optimization, running procedures around the model, and so on. Also, AIMS provides a lot of functionalities for visualizing both the inputs and the output data, and also advanced deployment options provided by the AIMS Pro platform and the web-based user interface. So we are especially focusing here on the modeling aspects for facility location, and we will try to illustrate this more specifically by giving a number of examples. And in that we take the route suggested by Bose in his article, Can We Make Mathematics Intelligible?, where the idea is that generalizations are made by abstraction from experience, so based on just having various examples of the problems in this area. So the first example will be location of distribution centers. Here you can see a screenshot from AIMS, from the AIMS example, where you can see the model editor on the left top panel, also the progress window of the solver, and on the right hand side you can see the visualization of the solution. So in this problem, which is a kind of typical example, there are a number of plants that can produce two types of products. In this case we name them as gasoline and diesel, but it can be of course any two or several products. The location of the plants is known, and the plants have a certain capacity and a certain supply of products. Also, there are a number of demand regions. Their location is also known. These regions have demand data, and of course there is some known data about the transportation costs that are involved between the different locations. The intermediate layer of this network is represented by distribution centers. So the products will be transported from plants to distribution centers, and from distribution centers to the regions that demand this kind of products. All right, so it's a typical example. It's a multi-commodity network flow problem. So one of the main variables in this problem is the commodity flow, which you can see at the bottom of the screen. In this case, the commodity flow is a variable that has 4 dimensions. So C is the index of commodities, and then we have the indices of the 3 layers in our network. So P for plants, D for distribution centers, and R for region served. This variable, of course, appears in the total cost, which is the objective of our model. But next to that, the objective also contains fixed throughput, fixed cost for the selected depots. So these depots which are selected will have fixed throughput costs. And also there are some transportation costs that depend on which region is served by which depot. And in order to deal with possible infeasibilities due to not sufficient supply, we also have a term that includes the add supply variable. This variable can be added to the model as necessary. So typical decisions in location problems are binary decisions representing whether or not a certain location is used. In this case, DC selected is a binary decision whether or not the corresponding DC is actually selected in the solution or not. But we also have a variable which is binary as well, region served, so with two indices, depot and region. So every depot in this situation, every region will be served by one depot, and this variable region served will in the end tell us whether a certain region is indeed served by a given depot. Well, then a typical formulation of constraints in our model is, for example, supply constraint, which just says that for every commodity and every production plant, well, the total amount shipped to customer regions via a distribution center, via all the distribution centers, cannot be more than the available production capacity of that plant. But here it's also it can also be seen that add supply variable is added, so this add supply variable plays here a role of slack variable. So in case that actually there is not enough supply to satisfy all the flow, so we can add this option to have additional supply, which in the end will add also some higher costs to the objective function. Demand constraint says that well, for every commodity in each region, the demand should be satisfied by the commodity flow that comes from all the plants. Of course, region served variable, which is a binary variable, then appears as well in the right-hand side. So we can only satisfy demand of a certain region if that region from a distribution center, if that region is indeed served by that distribution center indicated by the binary variable. Of course, other constraints are flow balance constraints. So for example, at each distribution center, the incoming flow should equal the outgoing flow. And there are also constraints on the maximum throughput at the distribution center. So if a distribution center is selected, then the amount of flow through that distribution center cannot be more than the maximum throughput capacity. So I will try to demo how to make the analysis of a location problem using this AIMS project. So again, you can see here the model part with the variables and constraints that we have introduced. And you can see also the progress window of the solver. And on the right-hand side, you can see the visualization page for the network flow. So if we allow all the distribution center, potential location of the distribution centers to be choosable in the solution, then we can solve the problem. And once we solve the problem, the selected distribution centers are then highlighted in the network, and also the commodity flows are shown from plants to distribution center and from distribution center to customer regions. Well, we can also show, by one click, we can show the actual flows on the network arcs. So for example, we can see that plant 1 has 15 units supply of gasoline, which is represented by the orange arcs. So 9 flow of 9 goes to DC2 and from DC2 to region 2, and a flow of 6 goes from plant 1 to DC4, and from there it goes to region 1. Of course, region 1 also gets 2 units of gasoline via plant 2 and then DC4. So every region is served by one distribution center, but the distribution center itself can receive flow from more plants. All right, so this is how the solution would look like. Of course, we can represent which region is served by which distribution center, so we can show that in the table on the right. Or we can also show either in a table or in other graphical objects, we can show the actual flow. For the moment, let's switch off the flows on the network itself. So what kind of analysis we can do with this kind of model? We see that now we solve the model with all distribution centers, and the total cost is 859. This would be the cost when all the potential locations are allowed. But what if one location, for example, is not allowed? So we can just exclude this distribution center 5. We do not allow it anymore to be a choosable location, so then we can resolve the problem. Now we can see that DC5 is no longer part of the solution. Instead, DC1 has been selected. But of course, also the total cost has increased to 890 because now we have less choices for the location of our facilities. So this would be the kind of analysis that can be made. Of course, if the number of distribution centers is very large, maybe the selection of distribution centers that are allowed cannot be always made in a selection object, but it can be definitely made using the procedures in AIMS. So the idea is that we have a set of allowed distribution centers, which is a subset of all the potential distribution centers. And this is determined by a binary indicator, whether DC is allowed or not. This is a typical construct with which you can create subsets in AIMS. And these subsets can be either then manipulated using graphical objects, or they can be determined using procedures. All right, so let's allow again all the distribution centers. So we go back to the first solution. What other type of analysis can we do on this using this model? For example, what if the supply, for example, of gasoline at P1 drops just 1 unit? What happens in that case? So if we want to solve, then we get the message that the solver concluded that this problem is infeasible. And of course, it's infeasible because there is not enough supply to satisfy all the demand. But in that case, we can just check one box. If we check this box, the effect will be that the add supply variable is actually added to the model, more specifically to the supply constraint, and by that we introduce a slack. So if we resolve the model in this case, the model becomes feasible, and we see that the additional supply that is necessary amounts to 5 units at plant 1. So if, for example, this supply figure would be increased from 1 to 6 and then resolve the problem, then we see that the model remains feasible and we don't need any additional supply, which we can get only against higher cost. But we can satisfy it all from the supply available at P1. So again, we can always show the flows on the network and then analyze what the effect is on the solution. If, for example, we reinitialize the situation in the first place, solve, then we have again the initial solution. But we can also analyze, for example, what happens with the solution if one of the distribution centers has lower capacity. Say that suddenly we don't have 21 throughput capacity available, but we only have 10. So then we can resolve. What we see is that DC5 now it's still allowed as a choosable location, but it's not used because the capacity is too low. So if we resolve the problem, then we see immediately that another distribution center has been chosen. Of course, every time we run such an experiment, we can analyze what is the effect on the total cost. All right, so this is a first example which shows how you can use the modeling concepts in AIMS and also how you can use the graphical representation of the solution in order to actually make an analysis of the location problem. So the idea is that just solving one instance of the model is of course not sufficient. So for actually supporting a decision-making process, we need to have all the means available for analyzing various scenarios, various situations to be able to exclude potential location or change the supply and demand data of the problem, and then re-optimize efficiently and analyze the solution. So this would be a first example. Another example that I would like to discuss is from the area of postal logistics, so location of postal depots. Again, on this slide, you can see the model part, the progress window, and a simple visualization of the solution. In this case, we also have three layers: factories, depots, and then postal codes that need to receive mail bags. But the difference is that the flow from the factories to depots is usually large, and it's measured in number of rides between a factory and the distribution and the depot. So the main difference here is basically that the number of rides between factory and depot is also a binary variable, and also the number of small rides between depot and the postal code is again a binary variable. It's an integer variable, so the number of rides can assume integer values. Of course, the objective function contains the fixed cost and then the cost associated with the number of small rides and the cost associated with the number of large rides. So, as in the previous example, we also have here a binary variable whether or not a depot is used, but the main difference is that the flow is actually measured by integer variables in how many rides are performed between two sites. Also, there are constraints on the flow variables. So the flow transported amount cannot be more than the number of rides multiplied by the maximum capacity of one ride. And there are also constraints on the depot capacity. So if in the case a depot is used, the amount of transport to the depot or out from the depot cannot be more than depot capacity. And there is also the usual conservation of flow constraint. So I will also briefly demo this project. So again, we see here the model explorer representing the model and the input parameters. In particular, for example, the costs. The costs are computed here based on, for example, what are the costs per hour for a large ride, and what are the costs per kilometer of a ride, and then multiplied by either time or the distance. So cost per hour times time and cost per kilometer times distance. where the input parameter are just read from Excel using our integrated Excel library. So we just read the data from Excel. Then we have the data of all these costs. And once the costs have been determined, we can run the optimization. Again, solved by a Cplex, and afterwards we can see on our results page, we can see which depots have been chosen, the number of rides, large between depot, so originating from that depot, or no, the number of large rides going into that depot and the number of small rides going from depot to postal codes. Of course, we can also determine the costs for large rides and for small rides, and also the total flow amounts from to the depot or from the depot. We can, of course, also compute the data for the factories. In this case, we have 2 factories, and then we can show, for example, in the first diagram, you can see that for every depot, there is some number of rides going from the two factories to the corresponding depot. So, for example, if we go from Westzaan to Amsterdam, there are 3 rides. And we can also show the total amount of transported in number of mail bags from factory to the depot. Of course, this is quite simple analysis that can be done, but more complex visualizations can be done in AIMS, and I will come back to that later on. Moving on, I would like to present yet another example, so location of production plants. This is an example inspired from one of the projects that we did. So in this case, we have a European network where different postal codes have to be supplied by some existing plants and also possible new plants that produce, in this case, some energy efficient systems for buildings, and they have to be shipped between plants and the postal codes. The main challenge here is that there are very many postal codes that represent demand points. So it's a challenge to consider them all at the same time, and also that the decision maker would like to maybe make a pre-selection of all the potential locations for the new plants. So the network structure looks like this. We have existing plants for which the capacity is known, but it can also be increased. And we have new plants that can be located at so potentially at any of the location of the zip codes, and every zip code can be then the demand of every zip code can be then satisfied either from an existing plant or from a new plant. So this is a capacitated location allocation model, but there are various options for expansion of existing capacity and additional site constraints. What is different in this case from the previous examples that I presented is that the objective is to minimize the total traveled distance. So that means in general transport times distance, but more formally, so we have in the objective transport times distance for the existing plants, which is the first term, and also transport times distance for the new plants. For the existing plants, the transport variable only has two indices, namely the plant and the zip code. But for the new plants, we need to include three indices because every new plant has a specific capacity, and each new plant can be then located at any of the allowed zip codes. So zip code NP denotes the index of all the zip codes that allow new plants. And this variable has then to be multiplied by the distance between, well, the zip code of the new plant and the zip code that receives shipments from the corresponding plant. Also, a performance indicator in this case is the overall weighted distance traveled. So that would be more or less the objective as about, but then divided by the total amount of transported products, either from an existing plant or from a new plant. So in this case, the weighted distance will be the average distance that one product travels weighted by the weights given by the transportation amounts. So in this case, there are several questions that need to be answered. Which existing plants to include or exclude? Should capacity of existing plants be expanded or reduced, and if so, how much? Should the location of new plants be considered, and in that case, which specific location choices to allow for the new plants, which is a very important question because there are so many possible locations. So the main challenges are that this can result in a very large-scale problem. There is an extremely large number of demand points and very many potential locations for new plants. So in this case, the challenge is not to have a model that includes everything in it, because that model would be actually not solvable on a regular machine, but to provide some kind of approach in which the end user or the decision maker can easily choose between different potential locations and also rerun some kind of boardroom analysis. So, for example, provide means to consider or don't consider specific existing plants, allow or don't allow a location of new plants, and more importantly, select specific location choices where the new plants can be located, and also maybe to tune in the accuracy of the solution process. So minimizing the total distance traveled, we have here an objective function which is sum of transportation time distance for existing plants, and in the case that we allow new plants, so that is the second term of the sum, depending on the indicator, allow new plants. If this indicator is 1, then we also include the term for the new plants, which means summation of transport type distance for the newly located plants. And well, as mentioned before, transport from the new plants has in this case 3 indices. The index of the new plant itself, because then we can consider different capacities corresponding to different plants, but also the index of the zip code where the plant should be located, and then the index of the zip code that is supplied by the new plant. Also, the model can be organized easily in 3 parts, such that the sets of variables and the constraints that we include in our model can be easily determined based on the 3 model parts. So AIMS, for example, allows you to take the intersection of the set all variables with some section in your model, like all variables intersected by model part 2 will result in the 3 symbolic variables declared in model part 2 section. Of course, in the same way, we can also determine the set of constraints. This is important for the analysis because depending on the choices that we make in the graphical user interface, that is depending on allow new plans or limit to one supply plant, so that every zip code is supplied by just one plant. Depending on these indicators that are driven by the graphical user interface, we can also drive which variables or which constraints then are included in the model to be solved. Again, location decisions are represented as binary variables, and here we can also use what is called in AIMS domain conditions. So domain conditions are additional logical conditions that can be applied on a variable such that you can limit, you can confine the number of index combinations that in the end will be generated into the mathematical model. And well, we also have binary decisions specific to this problem, like whether or not a zip code is to be associated with a certain existing plant or associated with a new plant. And of course, we have again supply and demand constraints, but also in this case, for example, the meat sales, so the demand constraint will include some terms of the new plants only if the new plants are allowed. So for this reason, the second term in the summation is formulated using a conditional if statement. So of course, we also have capacity constraint in this case. I will now try to demo how can we make a model-based analysis for this situation. So if no new plants are allowed, then we can just uncheck a box, and then we are left only with the existing plants that are considered into the model. We can choose the tolerance of the solver. In this case is set on 2% relative optimality, and we can solve the problem using just existing plants. In this case, we can compute so the total distance travel, which is in the order of 205 million, and the overall average distance traveled is 455 kilometers. If we allow new plants, so we can do that from the graphical user interface just by checking one box. Suppose that we now allow just one plant. This new plant can be located either in one of the existing countries, and then we have to choose, for example, one country. So if we choose a country, European country, in that country we have a number of potential locations, and well, in this case we can then resolve the problem where a new plant will be located in Cyprus in this case. Solving the problem results now in different total distance traveled and also different weighted average distance. And if we, for example, do not want to limit the new location to one country, well, then we can select some zip codes, one for every country. Of course, these zip codes can be also selected or deselected in an easy way, and then resolve the problem where now the plant has to be located in one of the potential locations that we have selected. So in this case, the problem becomes more challenging than in the situation that we've chosen Cyprus, where there are only limited locations. And in this case, we can see that, well, we have a lower weighted average distance, which is our key performance indicator. Of course, we can show also the results, like what are the new plants, where are they located. In this case, well, the location results in the zip code in Ukraine. Of course, the next level would be if you allow two or several new plants to be located. If we allow two new plants to be located everywhere at the selected zip codes in all the countries, well, this situation can be also solved quite quickly, but it will take about 2 minutes. And for that reason, I have here already the solution. So with two plants, it takes about 2 minutes to solve the problem. And in this case, we can see that the total the weighted average distance traveled then drops to 413, and also the total distance traveled drops to 186 million. So, of course, it's possible to also change the capacities of the existing plants or the capacities of the new plants and rerun the analysis in the same way. The main idea again is that solving one instance is not sufficient, and we need to perform the analysis on several scenarios and then maybe tune into the solution process and so on. But the results of the analysis in this case are that the optimized solutions are up to 47% better than heuristic solutions. We have a friendly tool here that allows for group interaction with the model, easy graphical selection of several options and several potential locations, and, well, a quick and insightful visualization, and we can get insight in various relationships between investment levels. And next, I would like to say a few words about more advanced options for visualization and deployment. So in AIMS, we start always with creating a model, then we import data from different sources. We use powerful solvers to construct our solution approach, and then we go into visualization of the results. And of course, this process is repeated several times, several iterations, until we reach a state where the application has a robust model and a very nice graphical user interface. So in that respect, we have the AIMS development part, which is the part on the left that I presented before, but we can also once the applications are developed, we can deploy them in the AIMS Pro platform, which is a client-server architecture where different users can just launch application from a central server, and there is an advanced way to do user management and application management. In that context, we can deploy applications both using a Windows-based user interface, as can be seen in this screenshot. So the type of location problems, for example, that are encountered in supply chain applications can be visualized in the end using this kind of graphical objects. And also, for example, we can build more information about the solution, about around the results of our problem. For example, showing what is the network structure, or maybe also dealing with time dynamics in case time is also involved if we have multi-period location problems. But next to the Windows-based user interface, when deploying AIMS-based applications in Pro, we can of course also use the web-based user interface where the visualization is represented in the browser, and so this user interface is no longer limited to Windows-based machine. So it can be also visualized in on tablets, on smartphones, or other devices. We have in AIMS various means to represent the solution, for example, using map widget, but also in order to visualize the results and make all kind of analysis of the solution. It's also possible to customize the web-based user interface and bring all kind of appealing features into the browser-based visualization. Well, this would conclude my presentation about the facility location topic. I would just like to add a few words more about AIMS. It's related to the topic presented, but it's also more general. So AIMS is an integrated and interactive modeling system. It can also support the deployment of applications both using Windows UI or Web UI, and it supports the complete optimization or prescriptive analytics chain, from rapid prototyping to large-scale deployment of real-life applications. And this is completely in line with, where our data-driven managers headed, namely, less use of historic trend analysis and forecasting, and less use of standardized reporting, but more using more data visualization, scenario development, and applying analytics to various business processes. Also, as illustrated in this presentation, so underlying beliefs behind AIMS are that solving one model is oftentimes not enough, so we need to create valuable information around the problem, like we've seen in the facility location examples. So, for example, by using integrated graphics, doing scenario analysis, by providing also in the end data connectivity for this type of problems, or extended algorithmic capabilities. So in the end, we also provide an optimization and collaboration platform which can be used for running applications, but also sharing ideas and getting insight that can lead to better decisions. And last but not least, it's important to maintain an ecosystem of experts, partners, community members in order to assure that the user will be successful. Well, we believe that these are all differentiating factors when doing prescriptive analytics with AIMS, which concludes my presentation. So thank you very much for your attention, and maybe we have some time left for questions.